Section 250.80 of the National Electrical Code addresses the grounding of service raceways and enclosures. Specifically, it states that metal enclosures and raceways for service conductors and equipment must be grounded. However, there's an exception. The exception pertains to a metal elbow installed in an underground installation of rigid non-metallic conduit. To qualify for this exception, the elbow must be isolated from possible contact by a minimum cover of 450 mm or 18 inches to any part of the elbow and therefore not required to be grounded. A proposed change suggests modifying this exception to state that a metal elbow wouldn't be required to be grounded where it's installed in a non-metallic raceway and is isolated from possible contact by a minimum cover of 450 mm or 18 inches to any part of the elbow or is encased in not less than 50 mm or 2 inches of concrete. The reasoning behind this proposed change is to align the exception with exception number 3 of section 250.86. The argument is that the protection afforded by 50 mm or 2 inches of concrete encasement should be considered equivalent to 450 mm or 18 inches of earth cover. Section 230.6 seems to support this concept, as it considers 450 mm or 18 inches of earth cover or 50 mm or 2 inches of concrete encasement suitable for considering service conductors outside of the building. However, the proposed change was rejected. The reason for the rejection is that the proposed text would allow a metal elbow to be used in a non-metallic raceway without grounding if it's encased in not less than 50 mm or 2 inches of concrete. This is deemed unacceptable because the concrete encasement doesn't provide a reliable path to ground. Furthermore, the proposed text would create a conflict with section 250.86 exception number 3, which requires a metal elbow to be grounded when it's installed in a non-metallic raceway. Therefore, the original requirement for grounding metal elbows in non-metallic raceways remains in place unless the specified depth of burial is met. The concern is the reliability of the ground path. While concrete offers physical protection, it doesn't guarantee a low impedance path back to the source, which is essential for proper fault clearing. In the event of a fault, a reliable ground path ensures that the overcurrent protective device, such as the circuit breaker or fuse, operates quickly to energize the circuit and prevent electrical shock or fire hazards. Concrete's conductivity can vary depending on its composition and moisture content, making it an unreliable grounding medium. Therefore, relying solely on concrete encasement for grounding is not considered a safe practice. Exception number 3 of section 250.86 addresses the grounding of metal elbows used to protect underground service entrance cables. This exception allows the metal elbow to be isolated from grounding provided it is buried at a certain depth, thus minimizing the risk of contact. The proposed change attempted to extend this exception to situations where the elbow is encased in concrete, but this was rejected due to concerns about the reliability of the concrete as a grounding medium. The primary goal of grounding is to provide a low impedance path for fault current to return to the source, thereby tripping the overcurrent protective device. This protects people and equipment from electrical hazards. The grounding path must be continuous and have sufficiently low impedance to safely carry the fault current. The NEC specifies the requirements for grounding and bonding to ensure electrical safety. Grounding and bonding are two distinct but related concepts. Grounding refers to connecting a circuit or equipment to the earth, while bonding refers to connecting different metallic parts together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety. In the case of metal elbows in non-metallic raceways, bonding is particularly important to ensure that the elbow is effectively grounded. Bonding the metal elbow to the grounding system provides a low impedance path for fault current, even if the concrete encasement is not a reliable conductor. The NEC provides detailed requirements for grounding and bonding in Article 250. These requirements cover various aspects of grounding and bonding, including the size of grounding conductors, the methods of connecting to ground, and the requirements for grounding different types of equipment. It is important to follow these requirements carefully to ensure electrical safety. When installing metal elbows in non-metallic raceways, it is essential to consider the grounding requirements of the NEC. If the elbow is not buried at the specified depth, it must be grounded to ensure electrical safety. This can be achieved by bonding the elbow to the grounding system using appropriate grounding conductors and connectors. The size of the grounding conductor must be determined based on the size of the circuit conductors, as specified in the NEC. In addition to grounding the metal elbow, it is also important to ensure that the non-metallic raceway is properly installed and supported. The raceway must be installed in accordance with the manufacturer's instructions and the requirements of the NEC. Proper installation and support will prevent damage to the raceway and ensure that the grounding system remains effective. It's worth reiterating that the decision to reject the proposed change highlights the emphasis on safety and the need for a reliable grounding path. Relying on the earth for meeting this path is more reliable than concrete encasement. The code aims to minimize potential hazards associated with electrical systems. This includes shock and fire. Firstly, grounding helps to stabilize voltage during normal operation. Secondly, in the event of a fault, such as a short circuit, the grounding system provides a low impedance path for the fault current to flow back to the source. Thirdly, this low impedance path causes the overcurrent protective device, like a circuit breaker or fuse, to trip quickly, interrupting the flow of electricity and preventing further damage or injury. The NEC requires that all metal enclosures and raceways containing electrical conductors be grounded. This includes metal conduit, metal boxes, metal cabinets, and other metal enclosures. The purpose of this requirement is to ensure that any exposed metal parts are at or near ground potential, minimizing the risk of electric shock. There are several methods for grounding metal enclosures and raceways. One common method is to use a grounding conductor, which is a wire that connects the metal enclosure or raceway to the grounding electrode system. The grounding electrode system typically consists of a ground rod, a metal water pipe, or other approved grounding electrodes. Another method is to use a bonding jumper, which is a short length of wire that connects two or more metal enclosures or raceways together. Bonding jumpers help to create a continuous electrical path, ensuring that all metal parts are at the same potential. The NEC also specifies the size and type of grounding conductors and bonding jumpers that must be used. The size of the grounding conductor is determined by the size of the circuit conductors. The type of grounding conductor must be suitable for the environment in which it is installed. For example, in corrosive environments, a corrosion-resistant grounding conductor must be used. In addition to grounding metal enclosures and raceways, the NEC also requires that certain types of equipment be grounded. This includes equipment that is likely to become energized, such as motors, transformers, and appliances. The grounding requirements for equipment vary depending on the type of equipment and the voltage of the circuit. The NEC provides detailed information on the grounding requirements for different types of equipment. It is important to follow these requirements carefully to ensure electrical safety. Grounding is a critical aspect of electrical safety. It helps to protect people and equipment from electrical shock and fire hazards. By following the grounding requirements of the NEC, it is possible to create a safe and reliable electrical system. When working with electrical systems, it is always important to take precautions to protect yourself from electrical shock. These precautions include wearing appropriate personal protective equipment, such as gloves and safety glasses, and using insulated tools. It is also important to de-energize the circuit before working on it. De-energizing the circuit involves turning off the power at the circuit breaker or fuse box. Before de-energizing the circuit, it is important to test it to make sure that it is actually de-energized. This can be done using a voltage tester. A voltage tester is a device that can detect the presence of voltage in a circuit. If the voltage tester indicates that there is voltage in the circuit, do not work on it. Find the source of the voltage and energize it before proceeding. When working with electrical systems, it is also important to be aware of the potential for arc flash. Arc flash is a dangerous electrical explosion that can occur when a short circuit occurs in the air. Arc flash can cause serious burns, blindness, and even death. To protect yourself from arc flash, it is important to wear appropriate arc-rated clothing and equipment. Arc-rated clothing is clothing that is designed to protect you from the heat and flames of an arc flash. Arc-rated equipment includes face shields, gloves, and other protective gear. Working with electrical systems can be dangerous, but by following the safety precautions and grounding requirements of the NEC, it is possible to minimize the risk of electrical shock and fire hazards. Remember that concrete can be subject to cracking and degradation over time, especially in environments with freeze-thaw cycles or exposure to chemicals. This can further compromise its already limited conductivity. This section of the code focuses on the protection of electrical systems from fault currents and the prevention of electrical shock hazards. The rejection of the proposed change underscores the importance of maintaining a reliable, low-impedance ground path for fault current return. Electrical codes are constantly evolving to address new technologies and safety concerns. It's crucial to stay updated on the latest requirements and best practices to ensure safe and compliant electrical installations. Always consult with a qualified electrician or electrical engineer when designing or installing electrical systems. Their expertise can help ensure that the system meets all applicable codes and standards and is safe for its intended use. They can also help you troubleshoot any electrical problems that you may encounter. In addition to following the NEC, it is also important to follow any local electrical codes and regulations. Local codes may be more stringent than the NEC in some areas. It is also important to follow the manufacturer's instructions for all electrical equipment. The manufacturer's instructions will provide specific information on how to install and operate the equipment safely. Remember that electrical work can be dangerous, so it is important to take precautions to protect yourself from electrical shock. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician. A qualified electrician will have the training and experience necessary to perform the work safely and correctly. When it comes to electrical safety, it is always better to be safe than sorry. In summary, when dealing with metal elbows in non-metallic raceways, adhere to the NEC guidelines for grounding. Ensure a reliable ground path. Consult with qualified professionals when needed. Your diligence will help to protect against risks. The proposal was not accepted due to a lack of confidence in concrete for ground. Always default to the code.